Hey everyone, welcome to this lecture on positron emission tomography. This one will mostly cover the background and the physics and the overall process of imaging with PET. The objectives for this talk are to understand the nuclear physics behind PET imaging, to describe the process of coincidence detection, to find the key terms that are associated with PET imaging, and label the parts of a PET scanner. First, we'll talk about how positrons are actually made, pair production and positron decay. They both occur in a neutron deficient nucleus, meaning there's not enough neutrons and there's an abundance of protons. There's a overly positive charge to the nucleus. So the proton will end up becoming a neutron. There's excess energy and charge in the nucleus, and those are released as a positively charged electron. This is a antiparticle for an electron. It has the same mass as an electron, but it carries a positive charge. And so this positively charged electron and a neutrino will be emitted from the nucleus. So the positron has the same mass and characteristics of an electron, but it does carry that extra positive charge away from the nucleus. So inside the nucleus, one of those protons will actually turn into a neutron, and it will kind of split into a neutron and then this positron particle, which has much less mass than a proton or a neutron, has the same mass as an electron, but it's carrying that positive charge away from the nucleus. So the mass will stay the same because there's the same kind of number of protons and neutrons together, but the atomic number will be less than 1 or -1. We have one less proton in the nucleus than we started with, but our overall mass is the same because you still have the overall number of nucleons in the nucleus. So there's a conservation of mass and charge when this type of decay happens. This is always followed by a secondary annihilation reaction. The positron carries a positive charge and is thus attracted to an electron. Because they are antiparticles of each other, one has a negative charge, one has a positive charge, so they're highly attracted to each other. They will collide with their full force with each other, and they will essentially annihilate. All of their mass will get converted to energy, and that energy is released in the form of 2 photons. So mass is completely converted to energy, and we have 2 511 keV photons that are emitted in opposite directions of each other. These are referred to as the annihilation photons. Beta positive or positron decay will occur when the neutron to proton ratio is too low for stability. Again, like I said, there's too many protons and not enough neutrons in the nucleus. And so as a way to regain that stability, it will convert one of those protons into a neutron as a positron particle is formed. Since a neutron is heavier than a proton, that there's a lot of energy that's required for that conversion. And this is also called positron emission or positron decay. Positron is a particle with the same mass as an electron, but it has that positive charge. This diagram is showing you actually what it looks like when they have positron decay. You'll see in this first nucleus over here, there's an unstable parent. You actually look at that, you can see that there are 6 protons and 5 neutrons. So it's lacking in its stability a little bit there. And so that proton will decay. And now if you count them, you have 5 protons and 6 neutrons. I had to take a minute to count there. But the proton will decay to the neutron in the nucleus, and now you have a positron and a neutrino that's emitted. The neutrino's right here. That's just there to really conserve mass. Doesn't really have a charge. It's just there to kind of conserve the laws of like E equals mc squared. And so you have to have mass and charge and energy kind of accounted for. And so the neutrino is there for that. And then you have the positron. And I want to show you that this is one where the secondary reaction is extremely important, because that's actually what we're imaging with PET. We're not imaging the positron decay per se, we're imaging this secondary annihilation reaction. So a couple really important things to pay attention to on this slide, not just the initial decay, but notice that that positron, it is going to be attracted to an electron. This is where they collide, and the two 511 keV photons go in opposite directions of each other. That's really important. That's actually what we're imaging. We're not imaging the positron decay, we're imaging the annihilation photons that come as a secondary reaction. Other thing that's really important I want you to pay attention to is the path that this positron takes. Of course, this is just a drawing. They're all going to be kind of unique. But this positron, remember, it's positively charged. Whenever you have a charged particle that's traveling through matter, it has a magnetic field. It has forces of repulsion and attraction acting on it. And so it's not going to travel in a straight line. It's going to kind of wiggle and twist and turn all around. And so this is the path that the positron will take. And the distance that it travels from the actual nucleus where it came from is called the effective positron range. That is very important. When it comes to applying this concept to imaging PET, you have a photon that's decaying. Let's say we give the person FDG and we're looking for cancer, and they have a small tumor. That tumor is going to take up the FDG. The FDG is decaying by positron emission inside the tumor, but we're imaging the annihilation photons. So these positrons travel in all different directions at this cattywampus path and eventually collide with an electron, and then they annihilate. So our camera picks up the annihilation photons and traces it back to the location where the annihilation happened or close to it. That's not actually where the radioactivity, where the positrons are. And so that's something that will degrade our spatial resolution with PET, because we're not imaging the thing that actually has the positrons, we're imaging the secondary reaction. And it's going to be important to keep in mind when we learn more about the PET radionuclides that different elements will have different energies and therefore different effective positron ranges. So some isotopes that we use in PET will travel pretty far before they have an annihilation reaction, and other ones don't travel very far before they collide with an electron. And so those ones that don't travel very far have better spatial resolution and better image quality in PET. And the ones that have a longer effective positron range tend to have a little bit worse spatial resolution on the images, because you'll have, the radioactivity in a tumor and you have all these positrons coming off of it in all different directions. And we're only imaging the annihilation reactions that happen. Since those are further from the nucleus, it's harder to really pinpoint a small tumor, pinpoint where that radioactivity came from. So this is the positron decay, but it does have a lot of implications for PET imaging. So remember, we're actually imaging the annihilation photons that happen a little bit of distance, and that distance matters. And also, they're not following in a straight path. Those are a couple important physics concepts to keep in mind as we learn about the PET instruments. And this chart is just showing you all the different types of radioactive decay that we talk about are applied to nuclear medicine. And positron is down here. And notice that the atomic number is unchanged. The Z number will decrease by 1. That means that their number of protons decrease by 1. So whenever you have positron decay, It actually decays to the element to the left of it on the periodic table. And this is the kind of diagram of it, the decay chart where it's showing you. F18 is one that we use a lot in PET. It decays by positron with an energy of 1.66 MeV, and it has a half-life of 109.8 minutes. You'll see that sometimes displayed as 109 or 110 minutes, but it's basically the same thing. And then you have a little portion of it, 3%, decays by electron capture, while 97% decays by positron. Remember, electron capture and positron are very similar. If you go back to that last slide, you'll see that both of them come from the same type of instability in the nucleus. If an element does not have enough energy to undergo positron decay, then it will undergo electron capture. A lot of positron decayed radionuclides will have both electron capture and beta positive. Sometimes the radioactive decay is pretty sloppy. In this case, only 3% is electron capture and the rest is positron. And so it ends up becoming O18, which is the element to the left of that on the periodic table. If you look at the periodic table, you have oxygen, and then fluorine is right next to it. And this is another PET radionuclide that's used pretty frequently. Germanium-68 is used in QC. It is similar half-life to cobalt-57. It's 270.9 days. Cobalt-57 that we use for gamma cameras is 270 days. So they have a very similar half-life. The germanium-68 decays 100% by electron capture. We have our PET QC sources that are germanium-68. For the longest time, that's all we used them for. But germanium-68 actually decays to gallium-68. Gallium-68 is interesting because it has very, very similar tagging properties to 99M technetium. You know that we use 99M technetium for most general nuclear medicine imaging because it's really easy to tag. It tags to a lot of different things. We can form a lot of different types of bonds or lignins and things like that with them, with technetium. And so it's a very ideal radionuclide for general imaging. Gallium is similar to that for PET because it can tag to a lot of different things. We can use it to tag to proteins and antibodies and all kinds of good stuff like that. We have gallium-68 PSMA, we have gallium-68 dotatate, and so there's a lot of things that we can use for theranostics and things like that because it will tag to those types of antibodies or antigens or proteins or amino acids and things like that. Very easy to tag. It has a half-life of about 68 minutes. I always remember that because 68 and 68, it's easy to remember that way. But gallium-68 is a radionuclide that we use to image. It decays by positron and electron capture, and it decays to 68 zinc, which is stable. And so that's just another one. But if you look at the periodic table, you'll see that gallium is to the left of germanium and zinc is to the left of that. So that's how it decays. This is another very common PET radionuclide. This is rubidium-82. That says 1.273 minutes is the half-life. It's actually, I always remember it as about 75 seconds, but it's something like that. It's just over a minute. And it's used for cardiac PET. Rubidium-82 is a analog of potassium. And so it's going to go to our muscles. That's why we are able to use it for myocardial perfusion imaging. It's really great for that. It has a little bit more complicated of a decay, but it decays by positron to Krypton 82, which is stable. And you can see here, it just has multiple energies that it emits, but they're all positron decay. So this is a purely positron radionuclide. And because the half-life is only 75 seconds, if you're using it for cardiac PET, you have to have a rubidium generator right beside the camera. You do QC in the morning to make sure it passes, and then the generator gets eluted straight into the patient and you image right away. Typically, if you spill rubidium, they say to just clear the room for about 10 minutes and it'll be decayed. So 10 to 15 minutes and it's gone through all its half-lives. So you would still, of course, want to survey, make sure it's gone, but those patients don't stay radioactive for very long. And then this is copper 64. Copper 64, as you notice, has one of these ones that has a little bit of a complicated and sloppy decay. Copper 64 is also known as DetectNet. For what we use it for, it can be used for a couple different things. It's being used for quite a few things in research, but the FDA approved radionuclide that we have for copper is copper 64 dotatate, under the brand name of DetectNet for neuroendocrine tumors. Copper 64 is interesting because it decays, has a beta negative and a beta positive decay. It's a interesting one, but the half-life for that one is 12.7 hours. So copper 64 has a very short effective positron range. You'll notice it doesn't have as much energy as some of the other ones did. And because it has a little bit less energy, it doesn't travel as far before it annihilates. So it has a short effective positron range. That's beneficial when we're imaging with it because that means that it has better spatial resolution. So if you're looking at a gallium 68 dotatate and a copper 64 dotatate, that copper 64 is going to have better spatial resolution, and it's also going to find smaller tumors a little bit better because of that better spatial resolution than the gallium one would. And we'll talk about that more when we get to talking about PET procedures. But that's very interesting benefit of using copper 64. One thing that I do want to point out, though, is that half-life is really long compared to our other PET radionuclides. And so that's something to consider with copper. You have to use a smaller dose because you have a larger radiation dose to the patient because it stays in their body longer. And then also, because you're using a smaller dose, it takes longer to do imaging. You have to take the images for about twice as long as you would for other radionuclides that are decaying faster. So on the periodic table, remember I said fluorine decays to oxygen, and rubidium actually comes from strontium, but if you go back up here, it decayed to krypton. That's what I told you. I think that's what I said. And then it has, also look at the columns. Rubidium acts like potassium. So that's something to keep in mind. Fluorine, choline, bromine, those kind of are very similar. And then we also had the copper and the gallium that we talked about. Gallium came from germanium, and then it decays to zinc. So notice they're all right there in the same line. Copper that we talked about decays to nickel. And so you see copper and nickel are right next to each other. So whenever it undergoes electron capture or positron, it becomes the element to the left of it on the periodic table. Now, when it comes to actually imaging with PET, we use something called coincidence detection. After the positron and the negatively charged electron undergo that annihilation, their rest masses are converted to a pair of annihilation photons. So this is that collision that I told you about. All their mass gets converted to energy, and we have the two 511 keV annihilation photons. Those are emitted 180 degrees from each other. Now, we say that, but it's traveling in waves and things like that. It's not going to be perfect 180 degrees but for the sake of argument, that's what we say. It's 100. They go opposite of each other. This occurs within a few tenths of a millimeter from the origin. Remember, that's where the effective positron range comes into play because sometimes it is a little bit further away than that. And then the annihilation coincidence detection is a near simultaneous detection of the two photons to localize their point of origin. This is the diagram of a PET CT scanner. So you notice that the CT scan is always first, and then the PET rows of detectors are behind that. Patient bed, patient goes into the scanner that way. They could go feet first or head first, that doesn't really matter. The CT is typically performed first, and that is done to get the scatter correction, the attenuation correction, the patient-specific attenuation mapping. All of that is acquired first. It's data that's extracted from the CT map that then gets applied to the PET images when the PET images are reconstructed. And so the CT is performed first, and then the PET study, the CT gets applied for iterative reconstruction purposes and things like that to the PET images. Now, most of the time, the patient will get their CT first. But if you're doing diagnostic CT and the patient is getting their diagnostic CT and their PET scan at the same time, if they are getting contrast with their study, then you would want to do a quick attenuation correction CT before the PET, and then do the CT with contrast after the PET scan. And that's because the density of that CT contrast can impact and create artifacts on the PET images. And so you just do the CT for attenuation correction with the low dose first, and then do the PET study, and then do the diagnostic CT with contrast. But that doesn't really apply to most cases. Most of the time, you're just doing it for attenuation correction, and so the CT would come first and then the PET. It's just another diagram that shows you how it works. So you have the tumor that actually has the F18 in it, and then that positron follows a disorganized kind of wonky path. It hits an electron and they annihilate. The two 511 keVs come off, and then they hit these detectors that are opposite each other. In this drawing, I want you to notice there's a red line here. That red line that goes around and connects those two detector blocks, it's basically showing you that those detectors have to be able to communicate. So in the back of the PET scanner, it's just a whole big mess of wires and circuit boards and things like that, because all of these detectors communicate with each other, and especially the ones that are opposite of each other. And that is very important for us to actually be able to take the images. And then, of course, the images get taken that way. Now, time of flight is another important concept with PET. This has improved coincidence imaging. I want to really reiterate to you guys and kind of drive to home that this is not a replacement for coincidence imaging. It's an improved version of it. And so PET works by coincidence imaging, where you have to have the photons opposite each other for it to count as a count. But time of flight helps us better locate where those photons actually came from. So in theory, it is possible to determine the location of the event, meaning the annihilation event, by determining the time difference between the photon detections. This allows for tomographic reconstruction without mathematical algorithms. Now you do have some, but it's improved process. And so this achieves timing accuracy of picoseconds. Think about that. How quick are our technology has become and how improved our technology has become that we can chase single gamma photons within picoseconds of each other. And so that is extremely important, huge improvement in PET. All PET at this point is time of flight PET, unless you have a super old, ridiculous scanner. But this sometimes leads to increased signal noise ratio, but this is improving greatly. We've made great strides with time of flight. And so what happens is you have, these annihilation photons, and they hit this detectors that are opposite of each other. And typically when that happens, as soon as the camera says, oh, there was two photons that hit opposite of each other, it creates a line of response. And we say, okay, there was a count somewhere along that line. Time of flight uses the time difference between when it hit one side and the other to say, okay, it hit over here a little bit quicker than it hit over here. So based on that time difference, it must be located at this particular spot along that path, because it's going to hit the one quicker that it's closest to, and it's going to take a fraction of a second longer to hit the opposite side. And so that's how time of flight works. It uses that time difference within a picosecond to trace exactly where that came from. It's not exact. I know I just said exactly where it came from. It's not quite exact, but it's very, very close, and it has improved spatial resolution and detection accuracy and things like that. So at this point, all PET is time of flight unless you have a scanner that's like 20 or 30 years old that you're still using. All right, spatial resolution is determined by the size of the detector elements and the internal resolution of the camera. Remember, this is also influenced by the effective positron range, how far that positron travels. But from the camera standpoint, it's the size of the detector elements and the internal resolution of the camera. This differs from SPECT. SPECT is very reliant on collimation, and PET is not. With PET, all of it is electronic, and so we don't have collimators like we have with gamma cameras, and we do it all electronically with that timing and the coincidence timing. Because our collimators are filtering out photons that come from wonky angles. You have a row of detectors around the patient with PET, and you're relying on these photons hitting opposite of each other to determine whether it counts as a count or not. So they have to already be coming from straight on, because there has to be a pair on the other side. And so because of that, we don't need the collimators like we have in the gamma camera to filter out photons that are coming from funky angles. Because let's say there's a scattered photon that hits here, but its mate is over here. It's gonna not, neither one of those are gonna count because they don't have a pair on the other end. And so we say it's electronic collimation because it has to be a coincidence event. It has to be two photons hitting opposite of each other for it to actually count. So it already has to be straight on, or sort of straight on. So a couple things that degrade the spatial resolution, like I said, that effective positron range. This is the finite range of a positron. It's not the exact location of the event. And the effective positron range is the average distance from an emitting nucleus to the end of the positron range. So that's just the average. It's never gonna be exact, because you have all of these positrons that are decaying off of all of these atoms, and they're decaying in different, the positrons are going in different directions. They're encountering different tissues, different tissue densities. They have slightly different path because they're being pulled electromagnetically by different tissues or different elements that they're coming into contact with. And so it's never going to be exactly the same. And so we use the term effective positron range, which is kind of like the average distance that positrons will travel, knowing that some of them won't travel as far and some of them will travel further. But we go by that average, that effective positron range. So every PET radionuclide has an effective positron range. If it has a higher effective positron range, whoops, I can't abbreviate properly. There we go. If it has a higher effective positron range, it means it's going to travel further. So it'll have less spatial resolution or worse spatial resolution. If it has a short effective positron range, that means it's not going to travel very far before it annihilates, and that will lead to improved spatial resolution. So like I said, when it comes to like neuroendocrine imaging, we have gallium dotatate and we have copper dotatate. Gallium has a higher effective positron range, so it has slightly less spatial resolution, whereas copper has a really short effective positron range, and therefore it has better spatial resolution. So some of those things come into play when we're choosing which radionuclide to use. When we have prostate imaging, we have quite a few PSMA agents. We have a couple that are gallium and a couple that are F18. F18 has a shorter effective positron range than gallium does. And so the F18 agents have a slightly better spatial resolution because of it. And then another thing to consider with the spatial resolution, the physics kind of influences that, is the non-collinearity. This is an important term to remember. The annihilation photons are almost never emitted at exactly 180 degrees from each other. Even if they were at exactly 180 degrees from each other, they're still traveling in waves. And so judging on where they hit, they might be a different part of their wavelength when they actually hit the detectors. And so they're never going to be exactly 180. And then they're also traveling in waves, so that can influence it. But we call that non-collinearity because they're not exactly opposite of each other. Plus, by the time they go through the patient and strike the detector, a lot of times they're not quite in line with their original origin anyway. So this is showing you the actual positron range. So this is the positron. It goes over here, this funky pattern, and then it annihilates with an electron. And so the actual range from the nucleus was kind of that linear line. But we call it the effective positron range is like the average that it would. And then you have the annihilation photons that come off of it. Since the actual range is not going to be consistent or exactly the same, that's why we use the term effective positron range. Positron range and non-collinearity create barriers for improving the spatial resolution of PET systems that cannot be overcome simply by using smaller detector elements. So remember, a lot of our influence on spatial resolution with the PET scanner is the detector elements and kind of the size of them and the internal spatial resolution capabilities of the camera. And it's going to have limitations to it based on our technology. But there's physics that we have to overcome that's really difficult. The positron range and the non-collinearity. That's something that's always going to degrade the spatial resolution, and it's just physics. We can't change it. We just have to know that it's there and do what we can to make sure that, we can advance technology, make smaller detectors, make it fast coincidence timing or time of flight, things like that, to try to improve the spatial resolution. But just because of physics, it's going to degrade it. And we have that with our regular gamma camera too, because our radionuclides will scatter within a patient, and that can make it difficult. We overcome that with collimators and things like that. But it's just something that you're going to end up losing some photons or losing some of your spatial resolution just because of physics. With the gamma camera, the typical sodium iodine thallium detector crystal thickness is about 1.25 centimeters or less. With PET systems, we use thicker crystals. We have to have thicker crystals with greater stopping power because instead of using like 140 keV photon, this is 511 keV photons. So it has a greater capability of just passing right through and never interacting with the crystals. So the crystals have to be thicker. They also have to be denser. We use much denser materials for the crystals in the PET systems. And then the depth of interaction effect says that the thick detector elements will decrease a little bit of the resolution. For a whole body PET scanner with a 4 millimeter wide detectors and a diameter of 80 centimeters, the DOI effect causes approximately 40% degradation of spatial resolution at a distance of 10 centimeters from the center of the field of view. You have less variation with hexagonal or octagonal detector arrays. A lot of times they've had squares in the past, or even circular ones in the very early days of PET, and that's just really hard to, you're going to end up losing some counts that way. This is just showing you that because of the width of the detector element, that when you do have annihilation photons or a coincidence event that happens opposite of each other, it really could happen anywhere in this shaded area. Means it could have come from anywhere in that shaded area. And so it has to consider the length of the detector elements, the width of the detector elements, and the diameter of the detector, or diameter of the actual scanner, and how far apart they are when it has to figure out where that photon actually came from. Another important thing to remember with PET imaging is that the coincidence imaging, kind of the way that we image them with coincidence imaging, it's going to lead to undersampling. Undersampling is a distortion of high frequency content or the fine details, and it results in over-processing an image. So this is just showing you, for A, it's a stationary array of discrete detector elements, and there's a linear sampling. In B, the linear sampling distance is reduced when the coincidence and immediately adjacent detectors are allowed. And then for C, for image reconstruction, these samples are treated as if they came from a set of virtual detectors. And so really what that's telling you is if you just sample exactly 180 degrees from each other, you're going to be missing some things. And so what it actually does is it even considers things where it hits the detector next to it and it's not quite exactly a straight line. And then when it gets reconstructed, it basically corrects for that and tries to figure out where those photons came from that way. So with PET, the selection of the filter type and the cutoff frequency depend on the study. That has a lot to do with considering the effective positron range, the energy of the radionuclide, things like that. Sensitivity affects the quality of the images and the amount of filtering that's required. Brain is best with a cutoff of 6, while the abdomen is better with 10 due to the amount of attenuation. And PET has a higher efficiency and can be processed with higher cutoff frequencies. This immediately helps us get better spatial resolution and sensitivity in our images. PET always has better spatial resolution, image contrast, and sensitivity over general nuclear medicine. Remember, we've talked about frequency before. This has to do with frequency of information when it changes from hot to cold really quick, from pixel to pixel, those quick changes from pixel to pixel where there's a lot of activity in one pixel, but then nothing in the pixel next to it. That usually indicates that there's anatomy there or pathology, right? There's something, our radionuclide went to this one pixel, but the one next to it has nothing. So that tells us it's the edge of the anatomy or it's the edge of some kind of pathology that's there. So all images are composed of a series of frequency waves. Remember, low frequency is when there's not a lot of pixel to pixel variation. You'll see that with background or with large organs. And then each image can have a series of low and medium and even high frequencies within it. Some of that is background, some of it is image data, and then some of it is noise. Noise has a tendency to be high frequency also because it will have sharp changes from one pixel to the next just because it's added junk or added kind of static that wasn't there before. High frequency has a large difference between pixel to pixel counts, and this would include images that have sharp edges like cardiac studies. And then low frequency has a very small difference in pixel to pixel counts, and you end up having less detail. Same kind of reconstruction technique applies to PET that applies to SPECT. The Nyquist frequency is really important. Remember, that's the highest frequency that it can do, kind of the limitations of the system. And the background is generated by back projection, mostly eliminated by a ramp filter. And then the image data can be lower or higher frequency based on the type of study. Noise is always high frequency, and this is unwanted. We do have a lot of noise in PET, but just because we have a lot of electronics and stuff, we have a lot of noise. But with PET, because you have coincidence detection and you have these line of responses, this is the filter back projection part where it creates a line of response and it uses the time of flight to help locate where that's at. That is a filtered back projection technique. That immediately gets applied as it's creating the raw data. Then you have your raw data that was created using filter back projection, and then the CT data gets added to it, and you have this iterative reconstruction. And so the final image was actually raw data had filter back projection applied to it, and then it was actually reconstructed with iterative reconstruction. So you have both with PET. Iterative reconstruction, though, is the thing that you're using to really reconstruct the images. This is kind of how the data is constructed in the first place and how it's acquired, and filter back projection gets used in that. But then iterative reconstruction is applied during the reconstruction step. And I know that's confusing, so just work with it, practice it, ask questions if you have them. So filtering is a trade-off between smoothing and resolution. Heavy filters will remove more data and create a smoother image, while light filters remove less data and result in a noisier image. You have a cutoff frequency, which is a lower value and a heavier filter. And this can be done in cycles per centimeter or cycles per pixel, or it can be the percentage of the Nyquist frequency, which is very common. So lower count studies will have more noise because noise is a greater percentage of the image. Noise is kind of fixed, but when we say more noise or less noise, it's more of how much noise you can actually see or actually contributes to the image. So it's kind of a greater percentage of the image. So if you have low count studies, noise becomes more prominent and a greater percentage of your count density. This requires heavier filters to smooth that out and get rid of the noise. If you have high count studies, the noise becomes much less noticeable. It's a lower percentage of the image, and so you can use lighter filters and still get good quality. Many quantitative programs require a special filter for proper analysis, and this is seen often in cardiac, where we have polar maps, ejection fractions, wall motions, all of these quantitative analyses that occur. The optimum filter depends on the study, patient, and the imaging, and then the parameters, equipment, and of course, physician preferences. Butterworth filter is the most common one. Now, what I've seen with PET is that a Gaussian, it's just the name of it, filter is what's most often applied. That's Gaussian. And that's the most common one that's applied to the PET during that like acquisition to create those images. But Butterworth is a family of filters for filter back projection. This used to be used in older PET systems, and if you, it's still mostly used in SPECT. If you have a really older PET system, especially if it's standalone, you may see that it's using a Butterworth filter, but it has an order and a critical frequency, whereas most other ones just have one critical frequency that uses as its cutoff. Iterative reconstruction can remove streak artifacts due to back projection. This is very subjective. It has 4 steps, gives you a rough estimate of the patient image, creation of projection profiles, comparison of the profiles with patient data, and then updating the computer image to reconcile the differences. Profiles can diverge with more iterations in creating artifacts or masking others. This is a very subjective guessing game. And you can make better image quality with iterative reconstruction than filtered back projection for less noise, better resolution, fewer artifacts, and less distortion. Recommendations for the number of iterations are made by the manufacturer. These are usually built into the protocols. You do have the ability to go in and change it, but these are manufacturer recommendations. And then it uses a 3D post filter to smooth the images. It can be used for SPECT, PET, or CT. And then if new to iterative reconstruction, you should also process it in the filter back projection and compare it. Sensitivity is determined by the absorption efficiency of the detector system and its solid angle of coverage of the imaged object. Sensitivity is still an important term to make sure that you know for all of our instruments. We talk about the useful field of view. We have a ring of detectors in which the individual elements are operated in coincidence with multiple elements on the opposite side of the ring. So what that's saying is you have this detector up here at the top. It can gather annihilation events from any of these detectors that are considered kind of opposite of it. And then same thing over here with this one. You have all these kind of detectors that are considered opposite of it. That's actually what makes up the useful field of view, or the useful, the useful field of view. So it can't kind of detect, once it starts getting there, it's really, you're not going to get any useful data from that. They're not opposite of each other. And so the useful field of view is really more in the center. As that coincides with all of these different angles and all the detectors, you'll notice that it creates this circle in the middle. And that circle is what makes up the useful field of view. The patient has to be in this circle, this useful field of view, in order for their images to be taken. So patient has to be in there. Because of that, as a technologist, when you're setting up the patient, you do what we call putting them in the ISO center. So you have to make sure that the patient bed is up high enough so that they're kind of in the middle, and then also line them up with the lasers to make sure they're in the middle. So the PET scanner has these lasers, laser positionings on them. They're on the side and on the top and on the outside of the scanner. And those are used to make sure that the patient is in the center, height-wise, and on this plane to make sure that they're centered. And that way, that ensures that the patient and all of the patient is in the useful field of view. That gets difficult if you're scanning somebody arms down and they're really heavy, because their body may extend outside of that all the way to the edge of the detectors. And that can actually create artifacts because their body's extending outside of the useful field of view. And as it reconstructs that, it's going to place those counts around the edges. And that's going to create what we call a truncation artifact. So event types, you have prompt coincidences. These are important to know. The prompt coincidences are just any event. When we say event, we're talking about the annihilation photons. So any events, any annihilation photons that happen opposite of each other within a timing window is called a prompt coincidence. From those prompt coincidences, then we need to decide, is it true, random, or scatter? True coincidences are true annihilation of pairs. This is what we want. This is where we know that these photons came opposite of each other. They hit within the timing window, and we know exactly where it came from. This is a true annihilation event. Then we have the random or accidental ones. These are annihilation photons from two unrelated events that just happen to hit opposite of each other within the timing window. They get reported as a pair. This is kind of like a false count, even though we don't call it that. But this is really hard for us to correct for because the instrument sees it as a true event. This is where you would have like one photon that is a true annihilation or from a true annihilation event, and it happens opposite of each other. But then on the opposite side, what you actually capture is a photon that's scattered from somewhere else in the body, and it just scattered within the body and then just happened to hit the detector opposite at the same time. That's going to create a line of response that's false, and then it's going to use the timing window to place that account along that line, but there shouldn't actually be one there. So this gets recorded as a pair, and it's really just two random photons that just happen to hit opposite of each other. And then you also have the scatter ones. This occurs when one or both photons undergo scatter, and they are detected in another detector. So scatters will sometimes end up being lost, but even if it's just scattered slightly, maybe they're not going to hit opposite of each other anymore, but those photons were scattered. It becomes difficult to correct for random and scatter and sort them out from what is true, especially the random ones. Randoms are very hard to filter out. What this scanner actually does is, we know statistically speaking, a certain percentage of all the counts we get will be randoms. And so it has a correction for that. And it has a scatter correction and then a correction for randoms that ends up getting applied to all the image data. Now the block detectors, the early scanners from the 1980s, very first developed ones, when I was doing my clinical back in the day, in the very early 2000s, I worked at a place that had one of the first PET scanners, commercially available, maybe the first. And so we had a very, very new generation scanner. And for those ones, there was a scintillator that was coupled to several PM tubes, and it created this detector block design. The advantage of that is that it allowed the detector elements to be decoded with only 4 PM tubes. Typically, you would have 4 PM tubes coupled to one single crystal, and that would make up the detector block. And then you would have a ring of detector blocks that went around the patient. So each one of them would have a crystal and then 4 PM tubes, and then all the electronics would come out of that. This is Siemens Biograph. So I'm going to show you a couple different types of PET scanners. The Siemens ones all kind of look the same. They're slightly different. Over here, you have a manual release for the table bed. The table moves on this track down here. You don't really want to pile things or step on that. If you step on it, you could break it. Same thing, I guess, if you're piling heavy things on it. Technologists always have a tendency to put the leg thing down there, but really you shouldn't. There are moving tracks underneath of here, and it's very important that you don't damage those or the table won't move in and out. Here's the laser pointers I told you about. There's one on the top and one on the sides. You want to make sure that the patient is in the center of the useful field of view. And then you have over here the controls. There's an e-stop button on each side. And then there's also all of those control pads basically have the information to raise the table up or down. Usually on the Siemens cameras, there's automatic QC button where it positions the table in the right place for the QC phantoms. And then you have, automatic where it will go down and into wheelchair height. So all of that. At the top, there's a screen. This is a cool feature on Siemens cameras. The screen mostly just tells you table height, where the table is, like on the Z-plane, how far in or out that it is. But it will also, if you have the patient pulled up on the acquisition computer, it will have the patient's name displayed. You don't want to get in a hurry and set the next patient up while the other one's still getting off the camera, because then you're displaying patient information to another patient. But it is a useful tool, so you can have the patient verify their name, and that way makes the patient feel a little better. They know you're doing the test on them and that you have the right information. But it's a useful patient identifier to make sure, yeah, that really is them. And it's one more way to check that you have the right patient before you start. Now, this silver ring that you see inside the gantry that I just wrote all over, that's where the CT component is. CT component, like I said, is always first. And then all this other space through here is there's several rings of PET detectors. And this width through here, how many rings of detectors you have for PET, that determines the bed position or how much you can actually do. So let's draw a little stick figure here. He's got his arms up above his head because he's getting a PET scan. He's really happy about it. And when you're actually scanning them, you have bed positions. So as you're planning your scan, it will look something like this. All the bed positions are the same. These are really your field of view, because you'll scan the patient in sections. And what that looks like is actually the different rows of detectors. So however many rows of detectors you have, that makes up one bed position. It's your field of view. And so you have to scan a patient in several bed positions. If you have a really big detector that has a lot of detector rows, then you're going to use fewer bed positions, which means your scans will go quicker because you can scan more anatomy per bed position. And so that's something that's really important to consider when you're getting a new camera, because it affects your workflow and how quickly you can scan patients through. The more bed positions you have to do, the longer the scan will take. Typically, we scan them by saying so many minutes per bed position. Most of the time, it's about 2 minutes per bed position or 1 minute per bed position. If you're doing copper dotatate, because you had to use a lower dose and it has a longer half-life, you have less counts coming off the patient. And so for that one, you would typically do 4 or 5 minutes per bed position. So that's kind of what the scanners look like. That's a Siemens one. Very good image quality, very reliable scanners. And then this is a GE Discovery. This setup right here is a QC holder. I think that's a QC holder. You have one that's similar for their head holder. If you're doing a brain, that might actually be what that is. It's kind of hard to see. Over here, you have a contrast injector. So this one is used for both. That's not like a Siemens GE thing. If the CT has enough slices and a capability, it can be used for diagnostic CTs. Same thing on this one though, you have a control pad, you have your lasers on the top and the sides, you have a little information screen up here that tells you the height and the I forget the word for that, but how far in the bed position is. This one, the table actually moves up and then in. So it's got a slightly different movement. Now what you can't see is over here on the end of GE beds is where it has the handle for the automatic or the manual movement of the bed to move the table in and out. So there's a manual one over there that you would have to grab and then you can slide it in and out. And then of course, same thing with the GE camera, CT's in first, and then all of this is the PET. The size of this circle is called the bore, and the gantry bore, what I mean is like the diameter in here within the ring, how wide that opening is, that's called the bore. That's important because you know, your bed could handle 450 pounds, but if you have a smaller bore in your camera, then the patient still might not fit. And even though you have this bore, you know, you might have space in there, the patient still might extend beyond the useful field of view. So just because they can fit in there doesn't mean you're still going to be able to scan their whole body and get good image quality. So that's something to keep in mind too. Some have a little bit better, a little bit larger bores than others do, you know, a little bit bigger gantries. And then this is the United Imaging one. United Imaging is unique because they use a lot of similarities with Siemens in their design. But United Imaging was the first to hit the market that was all digital PET. They use no PM tubes, they just have digital detectors. And because of that, they are maximized on their spatial resolution and sensitivity. You can use reduced doses and reduce your bed positions or your timing per bed positions. And so you can scan patients a lot quicker, but still get better spatial resolution and sensitivity in the images. They also have a longer kind of tunnel here because they have larger bed positions and larger field of views. And so you can image, you know, instead of doing like 10 bed positions for a person's whole body, you only need to do 4. And so it goes a lot quicker that way too, especially if you're doing 2 minutes per bed position and you have to do 10 beds. That's a 20-minute scan. But for the United Imaging scanner, let's say that same person, you only have to do 4 bed positions and you're doing 1 minute per bed position. That means that that patient's done in 4 minutes instead of 20. So that's huge for patients, huge for workflow. They're excellent cameras. They have a manual release on the bed down there. Table moves in and out, up and down, has a little track down here. And then the inside of them is very similar to Siemens. And this is the control panel for those. So that's the UMI 550. There's quite a few models of that though. United Imaging is also the one that has the total body PET, which means this extends the length of a person's whole body. I think it goes for like 6 feet or something. So the person literally just goes in the tunnel for like a minute and then they're done and you have their entire body from head to toe. So very interesting, very advanced and expensive camera. There are only a couple of those in the world. They're pretty new, but they were designed in California by a physicist there. So they're pretty cool. All right, and this is the detector block design with the when you do have the PM tube systems. So you have 4 PM tubes here. These are rectangular PM tubes. And then up here you have the detector elements. These are really small, but they're all because that is what's helping you with your spatial resolution, but also because these are very fragile and very expensive to produce. And so you have these small little rectangular crystals that are coupled together, and then they're coupled to 4 PM tubes, and that's what makes up one detector block. A modified detector block is where you have larger PM tubes to cover areas of other blocks. This is where it doesn't line up completely, and they actually share their quadrants. You have larger detection panels with less PM tubes. And again, this is what it looks like. You also have where it can kind of split that. You have scintillator 1, scintillator 2. These are all the crystals up here. And then you have the PM tubes down there. This is an example of quadrant sharing. For this one, the circles that you see are the PM tubes, and the square grid that you see is the crystals. So that's where they're quadrant sharing a detector. You don't see that so much anymore. You saw that with older PET scanners. Now they're more of the detector block design where you have the PM tubes coupled right to it. And this is showing you how it fits. This would be like one detector ring, and you have several of these rings that make up one bed position or one field of view. But in that, you have each one of these, you have the detector elements, and they're coupled to the 4 PM tubes, and that's one detector block. Translated over here, you have a whole ring of detector blocks, and then you have several rings lined up together to make up the field of view. Now the whole body scanner, like I told you about, super advanced. Most of them will have a ring diameter of about 80 to 90 centimeters with a bore size that's usually about 60 centimeters. This is the UMI Explorer. This is the only total body PET scanner that exists in the world. Like I said, it was developed in California by Dr. Simon Cherry, who worked out of Stanford. I believe it's Stanford. Yeah. And so you still have all the same manual controls on the bed and everything. It's just really, really large footprint. As you can see, this is a much longer table and a much longer scanner. The CT part in the front is the same. What's different is you have all these rows of detectors, and the patient will go in. You can scan their total body from head to toe in about a minute or so, and then bring them back out, and they're all done. So you can do a lot of patients that way. It's a lot easier on patients, especially ones that have trouble laying still. But that's how that works. And then these are some of the different designs of the detector rings over the years. So PET scanner geometries are based on discrete scintillator elements or continuous scintillator plates, like we have in the bottom. And so A is a full ring of modular block detectors. B is a partial ring. C is the hexagonal array. Blah, blah, blah. E and F are what you're going to see most often because it covers a bigger area. So this drawing is showing the transaxial, axial, and cross sections through the representative of the whole body scanner. And then this is a photograph of high resolution brain imaging system. You're not going to see a lot of these. This is a really old design. You can tell by the bed. The bed is on wheels and on a gurney. So you don't see that so much anymore, but this is the interior of the scanner. And so I wanted to show you what that looks like. Remember at the beginning, I told you there's a lot more wires and circuit boards. These are actually the detector elements that are closest. And in each one of these, you have the crystal and the PM tubes coupled. And then all the rest of this that you see out here is wires and circuit boards. And that's allowing those PM tubes to communicate that are opposite of each other or that are next to each other or sort of next to each other so that it can detect all of those annihilation photons. It has all the circuitry for the not just sequencing timing, but also the time of flight and the timing window to make sure that it was able to do that. The other thing that I just thought of is that I want you guys to know, remember in gamma camera imaging, we have a pulse height analysis and you have a window and a photo peak and things have to be within like plus or minus 10% of the photo peak. Well, with the PET scanner, you still have a pulse height analyzer and you still have a window and things like that. But with PET, we use a really, really wide window because it's more important to be able to capture those photons than to distinguish their energy. And as long as they hit opposite of each other, unless it's just really, really low energy and that it's for sure scattered, then most of the time it's going to count. So we have a really, really wide window, as much as a 60% window with PET scan imaging. But anyway, back to this picture. A is a dedicated brain scanner. It's a really small field of view. You can see that in B, that it's a lot smaller, but all those electronics are going to be the same as what you'd see in any camera. And then C is phantom images of that system. And you'll notice that it has much better spatial resolution. Spatial resolution is extremely important when you're doing brain imaging. You want a camera that has really good spatial resolution. So we also have some specialized PET scanners. We have high resolution ones for the brain and breast imaging. And actually there was a brand new dedicated brain PET system that just came onto the market. Has a really small field of view and it's a chair that a patient sits in. The chair actually moves up so that their head goes into this very small ring of detectors, and it's a digital PET system for the brain. And it's very, very small, just a chair. So that's really exciting new instrument that just came out, and people are buying them up in neurology centers and things like that because of the small footprint. They're able to put them in their offices of neurology clinics and things like that. Same with breast imaging, although it's not as common, there aren't a lot of them out there. They are really useful for patients who a mammogram is not the best choice. So mammograms are the gold standard, but for patients who have scar tissues, implants, dense breasts, then the mammogram is not that useful. And so in those patients, it's more useful to have PET or SPECT imaging. And then these have smaller diameter detectors, so they have much better geometric efficiency. And then the smaller detector elements offers higher spatial resolution. The tomographic reconstruction is done with iterative reconstruction, and the attenuation effects are reduced a lot more. This is a PET system for mammography. And so very similar to regular mammography, except there's no need to squeeze so hard. But the breast will fit right there in that space. It can compress a little bit till it's against it. And then it detects the photons coming off of it. And it creates a nice little image of the breast that way. You also have small animal PET scanners. These look like PET scanners for Barbie dolls or Bratz or whatever the little dolls are now. But they're very, very small, and they're usually used for mice. This is uses alternative detector technologies, very small scintillation detectors with positron sensitive PM tubes. There's lots of different designs, but they all look very similar. It's used for research studies and new radiopharmaceuticals or therapy agents. Everything is on a much smaller scale. This is a Siemens one, specifically for small animal imaging. We say small animal imaging, they're usually mice that will fit on there. And that little mouse would take up that entire scanner. And he just lay down there. They usually put them to sleep for it, put them under anesthesia or something, and then he'd go in and get scanned. It almost looks like a toy. It's on a little cart. There's a little P-scope for it, and they have great magnification as well. So all the little detector elements, PM tubes, a lot of them have the digital technology in them, and the little mousey will just go in there and get his whole body scanned. This is an example of what those look like. This is a little mouse micro pet. He had his little FDG study, and they were looking for cancer in him. These you can even do like the mice's brains or their hearts, or look for small tumors. So this is like a very old generation micro pet, but the one I showed you on the last slide is more of a newer one. They also have PET-MR scanners that are micro, that are made for mice, that are very cool looking. Now, one thing that's unique to PET is with our data acquisition, we have a choice between 2-dimensional or 3-dimensional. This is sort of like the acquisition modes that we have for gamma cameras that are like dynamic, list node, whole body studies. We still have that for PET, but we also have a choice of 2-dimensional or 3-dimensional. 2-dimensional is comparable to SPECT, where it rejects oblique photons, but 3-dimensional allows for those photons to count if they hit opposite of each other. This allows for a 4 to 8-fold increase in sensitivity because you're accepting more counts. So for 2-dimensional, you have a lower count rate, you have lower sensitivity, but you have better spatial resolution. With 3-dimensional, you're more sensitive, you have less resolution, but you have a higher count rate. This is electronic. We have electronic collimation with PET, and it's a software fix. We either decide we want to accept them or we decide we don't. This is part of the protocols where it decides if it's 2D or 3D. The times when you would want to use 3D is when you want to maximize your sensitivity and you have other ways of improving the resolution. This is where you want to get a really high sample counting rate. And a lot of times when we're using three-dimensional, it's on the brain because we want to really get the most sensitivity we can. Now, we also have data acquisition modes like dynamic or list mode. With this one, the detectors will surround the patient, they already are, and then they simultaneously collect the data. This allows dynamic studies in time frames of a few seconds. This is used for cardiac PET, especially the myocardial perfusion imaging, where we're getting myocardial blood flow, or we're getting ejection fraction, and we're getting that, we need that quantitative analysis. And then the whole body studies, this is a computer controlled bed. These are the bed positions that I told you about when we're scanning whole body PET studies. So the only time that we are not doing whole body PET is if we're doing the brain or the cardiac studies. But anytime you're doing oncology studies where you're doing the body, then you're doing a whole body study and it'll have multiple bed positions. So this is a computer controlled bed and it will just move through from bed position to bed position and incrementally, it's not a continuous movement, it incrementally moves down the patient. So let's say we started at the head, it will scan their head and then it'll move down. Let's say the field of view goes from the top of their head to their jawline. The bed positions need to overlap a little bit. So it would stay over the top of their head to their jawline for about 4 minutes. And then when it moves to the next bed position, it needs to overlap a little bit. So let's say now it goes from their lips down to their clavicle. So it included that little bit of their jaw again. There's a little bit of an overlap. So it does that just to make sure it's not missing anything and it stitches that together and then it actually corrects for it. Sometimes there's an error that you can see where it didn't properly apply those corrections and you can see the bed positions, but this is an image quality issue that would need corrected with the software. So that's something to keep in mind, but those bed positions do overlap. Now, I want to talk to you guys a little bit about the QC. We're not going to talk about that until next week, but there's something that I want you guys to keep in mind. With the regular gamma camera, when we talked about QC, most things are QC checks. The daily uniformity is a check. The weekly bar phantom is a check. The JZAC phantom, that's a check. Even pixel size, that's check. But some things are calibrations or fixes. The uniformity correction map that we do, that's a high count flood, that's a fix. That's a calibration. When we peaking the camera, that's a calibration. And so there are some things that we check and some things that we fix, that we calibrate. With the gamma camera, regular gamma camera, most of the things that we do as technologists are checks. But with PET, most of the things that we do are fixes. Most of the things that we're doing are calibrations. So there's also something called normalization, and this has a tendency to trick students sometimes. So just like the gamma camera, where we have a uniformity that we do daily, and then we have a uniformity correction, there's a normalization scan and a normalization calibration. Normalization scan is a check that we do every day. That's sort of like our uniformity. But the normalization that we do monthly, that is like a uniformity correction map. That's a correction, a calibration that we do. So I don't think your book explains that well, that there's a difference between the two. But the normalization that we do daily is a check. And it's similar to uniformity. It checks a few more things because PET is a lot more complicated than the gamma camera, but it's just checking it. The normalization think about it. With a regular gamma camera, you might have 30 to 60 PM tubes per camera head and one large crystal. But with PET, you have 10,000 to 20,000 detector elements, and all of them are going to have small variations. Just in our gamma camera that has one crystal per camera head, it's not uniform within that crystal. It's got a lot of issues already, right? And then when you have dual camera heads, it complicates it because the two camera heads need to match. But with PET, you have 10 to 20,000 of those detector elements, those little crystals. And every single one of them is going to have their own small variations. They're not going to be perfect when they come from the manufacturer. And so scanners are going to require corrections for non-uniformities and non-linearities. A lot of times when you're doing this, you're applying corrections and making sure that the corrections that were applied are still good. Any kind of poor correction is going to lead to rings on the images and artifacts. We can use a rod source to expose all the detectors to the same radiation source or the same number of counts. Scatter is also an problem. Those scattered annihilation photons get picked up and they will cause a fuzzy image because they end up looking like they're annihilation events and they get traced back with their line of response and a count gets placed in the field of view, but it's not supposed to be there. It's a false count or, false count that's showing up. It is impossible for the scanner to distinguish between scatter events in the body versus scatter events in the detector crystal on the basis of just the pulse amplitude. So this is best solved by fusing with CT and then correcting for scatter. CT uses that density map of the patient's body, and it can correct for scatters and also for attenuation. So the CT component is very important, and we'll talk about that when we get to hybrid imaging. Attenuation correction is the largest single correction that's made in PET. And older PET systems that are standalone PET will use a transmission source. And we talked about that when we talked about general tomography, but it will use a transmission source. So basically a source of radioactivity comes out and the patient actually attenuates that and exposes the detector. So before you scan the patient, you do a transmission scan using the patient. This exposes the patient to the radiation from that source, but it uses that to produce the density map. This is a rod source with its length extending along the axis of the scanner. It's placed in a holder near the surface of the scanner bore, and the holder rotates around the central axis so that the data are acquired for all the pairs. This is something that the scanners will do automatically. They'll have a robotic arm. Those robotic arms break all the time. And the robotic arm will pull out the pin or the rod source, and it will use that for the transmission scanning, and then it will retract back into the scanner, and the patient will be scanned from there. So that's only done in standalone PET, the transmission source, when you don't have a CT attached to it. It's kind of like an alternative way of creating a density map. Now, a blank scan is performed once a day. The blank scan is basically like our daily uniformity. It remains constant over time. You're testing the corrections and calibrations that you did and making sure that there aren't any non-uniformities or artifacts on the images. Dead time correction is also important. PET scanners will exhibit dead time and pulse pileup with high counting rates. Some systems will apply a global dead time correction. Other systems apply corrections to individual pairs of detector modules. There's low dead time corrections are best. Higher corrections are used for short-lived radio tracers like oxygen 15 that have an extremely short half-life. Noise equivalent counting rate is an important term when we talk about PET. This is roughly proportional to the square of the signal to noise ratio. Remember, the signal to noise ratio, signal is what we want, and the noise is what we don't want. So this is our ratio of the counts of radioactivity that are in the patient versus the electronic noise that's created by the scanner. So signal to noise ratio is important for all of our imaging. We want to have a really good signal to noise ratio. At higher activities, the noise equivalent count rate actually decreases because the rate of randoms increases as roughly the square of the activity. Dead time losses also reduce the observed counting rate. This is useful for comparing the performance of different scanners, and estimations of the noise equivalent count rate also can help guide the design. So this is something that is in like marketing material or they talk about when they're comparing scanners, because it gets kind of hard to compare sensitivity, resolution, temporal resolution, those kinds of things with a scanner. And so noise equivalent count rate is kind of like a blanket way of comparing all the different manufacturers and seeing which one is going to have a better count rate versus noise. Now, these last couple slides, I just want to show you the comparison between PET and SPECT and show you what some PET images will look like. So on the left, you see the PET image, and on the right, you see the same patient with SPECT. So I want you guys to pay attention to that and see that there are actually 3 different patients. So this is patient 1 and patient 1, patient 2 and patient 2, and then patient 3 and patient 3. So this is the control normal patient brain, normal patient brain, patient with dementia Lewy bodies, and patient with Alzheimer's disease. So look at them that way. Compare 1 to 1, 2 to 2, and 3 to 3. But anyway, if you look at that first patient, that's a control, that's a normal brain. And when you're looking at PET versus SPECT, notice that the PET has a lot better spatial resolution, and you have a lot more detail in the image. You can actually see some of the wrinkles in the brain in that first image. So PET is better in that regard. If you look at images 2 and 3 that are the same patient, you'll notice, in the normal brain, the brain looked great, it looked normal, but you did see a lot more detail with PET. I want you to pay attention to this patient that has Alzheimer's. This is the same patient. Notice that with the Alzheimer's disease patient, you see a lot better changes between hot and cold. You see a lot more accurate information and detail in the image. You see the disease a lot better than you see with SPECT. That has to do a lot with filtered back projection that we use for SPECT versus iterative reconstruction for PET. It also has to do with the CT map being applied to it, but most of it has to do with the imaging physics of PET and the capabilities of the scanners. It's just a lot different when you're trying to reconstruct and image that data. And so you get a lot better image quality with PET, hands down, than you ever will with SPECT. This is a comparison of, this is a PET bone scan. And this is an MDP regular bone scan. You'll see that the F18 fluoride versus the 99 MTEC MDP study, same patient, but I want you to pay attention here, especially to the detail in the spine. You see a lot more detail in the spine in separation of vertebrae in the PET patient versus the planar imaging patient. A lot more detail in the sacroiliac area. And then also, this is the same patient. You can see pathology. This is probably arthritis, but you can see some pathology in the PET that you didn't see in the planar. And that has to do with the improved spatial resolution. Your sensitivity and your resolution are improved with PET over general nukes, but you have a lot better spatial resolution that you can actually see those really small, tiny things that you can't see, the small, tiny elements with the gamma camera. So this person has quite a few areas where they have probably arthritis. It looks like in their ankles, their knee, that's not showing up at all in the same patient with the MDP study. So just showing you a comparison of the image quality with how much better PET looks. And then this is a cardiac study. Lot more artifacts with technetium versus rubidium because breast and diaphragm attenuation are just awful for tech-based cardiac studies when you're doing SPECT. But when you have like rubidium and you're doing PET, you don't have to really worry about attenuation from breast or diaphragm because especially when the CT gets applied to it, it automatically corrects for that. But also because you're imaging the 511 keV photons, they don't attenuate as well as the 140 keV ones do. And so you get a lot less attenuation, a lot less count loss. And so you inherently get better image quality that way. And so this was a patient that you have a lot more noticeable disease. It's showing up a lot more apparently because you can see the fine detail. Whereas this would have got reconstructed with filter back projection, which is noisier. And it has a tendency to sometimes place counts where they don't really need to be. Even though you see it kind of a little bit, it's not near as noticeable as it is when you look at the PET study. This one would probably get read as normal on the SPECT study, but on the PET study, it's very obvious that there's ischemia there. And this is the quantitative data. You guys haven't learned this yet, so don't pay too much attention to it because you haven't got there yet. But these are polar maps. That's quantitative data that's showing you the extent of ischemia. Where it's red, it's showing you that there's no ischemia. And you notice that it's really showing up a lot more on the PET study than it did on the SPECT. And then this is a comparison of Indium-111 pentatriotide. These are for neuroendocrine tumors. For years and years and years, we had Indium-111 pentatriotide, also called Octreoscan, and this was the only thing that we had to image neuroendocrine tumors. And then we got gallium dotatate or DOTATOC, and then copper dotatate. There's DOTATOC, dotatate, and DOTANOC out on the market, but they're all the same thing. And so these are basically the same drug, but tagged to a different radionuclide. So you can see the difference in the general oops, that's just a scribble. You can see a big difference with indium with the general nuke med versus the PET. These two are PET, and this one is general nuke med with a gamma camera. Indium is difficult to image anyway. It's got kind of some poor imaging qualities, not spectacular, but it's good. It's all we had, and so it was great for that. But now we have, this is the same patient, by the way. Now that we have DOTA-TOC and DOTA-TATE, this is a comparison between the two different PET agents. So first look at general nukes versus PET, and you'll see that there's a huge difference in what you're actually able to see. It's very kind of blurry, not a lot of detail. You see, like, you can kind of count the tumors there. There's like 1, 2, 3, 4, 5, 6, 7, maybe 8. But then you look at the DOTA-TATE and DOTA-TOC, and you notice that you get a lot more fine detail. There's actually like 1, 2, 3, 4, 5, 6, 7, 8, 9. And then you see all of this that you couldn't see before. Then you go over to the copper, which has better spatial resolution because it has a smaller effective positron range. And now you see more tumors in the chest, the side, down here in the groin that you didn't see before, even down here in the GI tract. And that's because this one has a smaller effective positron range, which means it has better spatial resolution. And both of them are good, but you notice the DOTA-TATE is a little bit better at finding those small tumors because it has a smaller effective positron range. So PET's a lot better. That is an limiting factor in some radionuclides like gallium, where it travels pretty far. And then the lutetium DOTA-TATE SPECT. This is actually lutetium DOTA-TATE is also known as Lutathera. That's a treatment for neuroendocrine tumors. And because it gives off a small amount of gamma and some Compton scattering, we can actually image SPECT with it and get those low energy photons. And this is just done to make sure that the therapy actually went to the tumor sites. And you can see that even though it's SPECT, so you're missing some of the fine detail in the image, you're seeing that it really did go to some of those areas. So general nuke, comparison of PET, and then the therapy. And this is the same patient in Octreoscan SPECT. So this is the indium-111 pentetriotide, also called Octreoscan. And then you have the copper-64 DOTA-TATE, also called DetectNet. These are looking for neuroendocrine tumors. Neuroendocrine tumors we haven't talked about yet, but they're very, very tricky to image and treat. They're known as a zebra because they will often mask themselves as other diseases or be asymptomatic until they look like this. So this is the same patient with Octreoscan SPECT versus the copper-64 DOTA-TATE. Notice that in the copper-64 DOTA-TATE, you really see a lot more tumors, a lot more small tumors than what you saw with the Octreoscan. You know, back in the day, the Octreoscan, we would have said, yeah, that patient is definitely positive. But when you look at the copper-64 DOTA-TATE, that just looks awful. So really a lot better for the patient at being able to see the fine details, the better spatial resolution, and the better sensitivity. When I say better sensitivity, it's because you're seeing a lot more of these tumors that are not being picked up at all on the SPECT study, at all these ones in the head. You're not seeing them at all on the SPECT study. So the test itself is not as sensitive at finding tumors because the imaging system is not as sensitive at finding the radiation. But with PET, it is. So you have improved sensitivity and spatial resolution over regular nuclear medicine imaging and over SPECT. So that's it for this lecture. I know it's kind of long, but let me know if you guys have any questions, and you can, call me, email me, whatever. Um, as you learn about PET, you'll learn more about the instrumentation this week. Next week, we'll go into the QC. There's a lot more to the QC because there's so much electronics, so much detector elements, and a lot of corrections that have to be made, and that you're always checking or recalibrating. So just keep that in mind, as you're learning about the camera and the QC next week, is that it's just a different kind of system. But because we're doing coincidence imaging and we're only looking at things opposite of each other, the detector elements have to be able to communicate effectively too. And so just keep that in mind going forward. And if you have questions, let me know. Thanks, guys.